Good afternoon, and thank you for coming. My name is Kostya Serebryany, and I'm from Google. I represent a team that develops and deploys various dynamic testing tools for C++ and other languages. I will have a hard time entertaining you after Andrei's talk, so I will probably try to scare you instead of entertaining. I love C++, don't get me wrong, but C++ has enormous amount of ways to shoot yourself into the foot, or rather into the feet. Buffer overflows, heap use after free, stack use after return, data races, deadlocks, uninitialized memory leaks, integer overflow, and I can continue this list for the whole hour. These bugs are scary in many ways. They're hard to debug, they're hard to reproduce, they lead to crashes, data corruption. But what many people forget, and they shouldn't forget, is the security. Many of the C++ specific bugs are actually security vulnerabilities. And if you don't care about security, you should. So I wonder if most of you have enough feet to use C++. Raise your feet who has. OK, so I would like to present 4 kinds of bulletproof boots for your feet. And then you decide if you want to wear them or be vulnerable. So I will be talking about 4 different tools which are similar in how they're implemented and how they work, but different in the set of bugs they find. Let's start with the first one chronologically. It is called AddressSanitizer, and it finds what we call addressability bugs. First, a short overview. The tool finds buffer overflows in stack, heap, and global variables. It finds heap use after free and also stack use after return. I will show examples later. It also finds a whole bunch of less interesting bugs like leaks, ODI violations, and so on. It consists of 2 parts. First is a compiler model, and we have implementations in both major open source compilers, LVM and GCC. The compiler model instruments all loads and stores in the program and inserts red zones around stack and global variables. And then the second part is a runtime library, which is basically a sophisticated Malloc replacement. It also does some bookkeeping for error messages. Let me bore you some examples, or maybe entertain, or maybe scare with some examples. So this is the simplest case of buffer overflow in a global variable. I couldn't come with a smaller example. All you need to find this bug in your program, just compile your program with Clang or GCC with 1 special switch and run the program. The tool is dynamic, which means that you actually have to run the program to find the bug. And if there is a bug during execution, the tool will crash and it will produce a very detailed bug report. In this case, it says global buffer overflow. It shows the stack trace where it happened, and it describes the global variable. Next example, a little bit more scary yet. Stack buffer overflow. The story is the same, with the exception that the buffer is on the function stack. The bug report is similar, except that the tool will show you the list of local functions, local variables in the function, and show you where you actually have accessed it out of bounds. Heap buffer overflow, same story, but now you have a stack trace of the allocation where the memory has been allocated before you used it incorrectly. Use after free. This is probably the most detail-rich report, which has like so many stack traces they don't even fit on this slide. You have stack trace where the use after free happened. You have a stack trace of where the free happened, or delete in this case. And you have a stack trace of the new or malloc invocation. Let's go to something more unusual, maybe. So consider you have a vector. You allocate vector of 8 elements, but then shrink it somehow. Either you resize or you pop back, so it becomes a little bit smaller. And then you access an element between size and capacity. So if you do it using operator brackets, everything is fine. A debug mode of STL will issue a warning or runtime error, whatever. However, vector has a very nasty C kind of thing, data, which allows you to export the guts of the vector. So if you use data, there is no protection from STL, and we provide this protection for you. On this example, we will show that you've been accessing a vector between size and capacity, and we'll also show you where this access is inside the vector. Even more interesting, and we start seeing these kind of bugs more and more, surprisingly, in a very heavy C++11 code. What do we have here? We have a local variable. We take its address and leak it somewhere to outer space. Then we return from this function, and we still continue using that address as if it was valid. It is valid to some extent. It is someone else's stack. And we can detect those bugs. Unfortunately, detecting those bugs is more complex, so we have to hide this feature under a runtime flag. Detecting these is roughly twice slower and requires more memory. But we still can do it.
Question?
Yes?
What in C++11 was causing more? If there's a simple answer.
Good question. What in C++11 is causing it? I think that more templates is causing it. It just hides the fact that you're using a reference out of scope from the eyes. This is like, I don't know why, frankly. Another interesting set of bugs, we call them initialization order fiasco. When you have two C++ or C modules, and you have two globals to them, one of the globals may depend on the value of the other global. This is undefined. This is undefined behavior. And it is often surprising to people, like, why does my program depend on the order of linking the files, right? We can detect this. Memory leaks are boring. We can detect them. And now let me describe. Yes?
I just point out that two jobs ago, the number one problem, the number one reason my library failed was because someone relied on file scope static initialization, runtime file scope static initialization, and they would come to me and say, your library is broken. And that was the reason. That was the number one reason. I'm just saying, that's huge. Just so you know.
This is indeed huge. How did we come to actually implementing this check? One of our compiler guys in Google has tried to build a huge application with a whole program mode optimization, so that all models got mixed together and like reordered, and nothing worked. and then they started debugging it manually and started finding these init order fiasco one by one in dozens. And so we've implemented this check and cleaned up the source base. So memory leaks are boring. However, they're quite numerous. We can detect them. Let me try to describe how this whole thing works. First of all, let me define what we call shadow byte. Shadow byte is actually a byte. And what do we use it for? Now, take your application virtual memory and take any 8 aligned bytes of your application. With regard to addressability, there are only 9 states of these 8 bytes. So either all are good, addressable, you can read, write, etc., or all of them are bad, non-addressable, or the first k bytes are good, and the rest 8 minus k are bad. And this is easy to enforce if all of your objects are 8-byte aligned. If so, you cannot have bad bytes first in your 8-byte word and then good bytes. So just 9 states. 9 is less than 256, and you can encode this value from 0 to 8 in a single byte. And that's what we call shadow byte. We have to store these shadow bytes somewhere for every 8 bytes of the application. And that's what we do. We divide the entire address space, the entire virtual address space of your application into several parts. Conceptually, there are just 2 parts. The memory that belongs to the application and the memory that belongs to the shadow. Unfortunately, we cannot do it physically because on Linux at least, there is some memory in the basement of the address space and in the ceiling of address space. So what we do in reality, we divide it into 5 pieces. 2 pieces belong to the application, 2 pieces belong to the shadow, and 1 small piece is completely protected, no one can go there. The good part here is that the mapping between 8 bytes of the application and 1 byte in the shadow is just 2 arithmetic instructions. Divide by 8 and add a constant offset. This is all. So what we do with this shadow mapping? We instrument a program at compile time. And when a compiler sees a memory access, either read or write, it doesn't matter, it computes an address of shadow that corresponds to this application memory. So we take the address, divide it by 8, and add an offset. Then we load a single byte from that shadow. And if we don't like this byte, we bark. And then go on. A situation for smaller accesses like 1 to 4 byte accesses is just slightly more complicated. It adds a few arithmetic instructions. And here, for those who like assembly, an example of the code generated by the client compiler. So the last instruction is the instruction that would have been originally in the code. This is a store of some constant to some address. We add just those 5 instructions. We save the register where the address is. We then divide it by 8. We then, in a single instruction, add an offset, load, and compare with 0. And if we don't like the value, we just bypass this jump and generate some kind of trap. It could be a function call, or it could be an instruction that generates some nice signal. And this is all, very cheap. Now we have to make sure that bad memory is actually marked as bad. We call it poisoned. Suppose we have a stack variable in a function. What we need to do is we need to put red zones around that stack functions so that we can poison the shadow that corresponds to those red zones. And that's basically how we do it. We don't do it on the source level, but we do it in the compiler. So we put a red zone at the left, we put a red zone at the right. They have some alignment requirements for better performance. Then we compute shadow of the red zones. And then we just put some special kind of garbage into those red zones. Note that the shadow is 8 times smaller. So if you need a 32-byte red zone, you only have to poison 4 bytes of shadow. This is very, very fast. 1 cheap instruction. So once you've poisoned the shadow for the red zones in the stack variable, you go on with the function code. And before you exit, you have to unpoison the whole thing. For global variables, we do even simpler. We just create a larger global variables with red zones at the right. And then we poison them at startup. Most interesting bugs are actually not globals and stack, but heap. Well, maybe not the most interesting, but the most frequent ones are related to heap. So for heap, we do all the same tricks. We insert red zones around every allocated chunk of memory at the right and at the left and poison them. Then, once the memory is freed or deleted, we actually try hard to delay the reuse of that freed memory so that it remains poisoned for a long time. so that we can detect use after free. And we also collect stack traces every time we do malloc and free, so that we can produce nice warning messages I've just shown you before. So this is a slide from my marketing department. The tool is extremely fast. It has 2x slowdown on average on a large variety of tools. Raise your hands, how many of you used Valgrind? Okay, so Valgrind it says to have 20x slowdown. Unfortunately, on Google applications, it usually has much more slowdown. First of all, because Google applications tend to be extremely huge and you pay much for binary translation. And then because Google applications usually heavily multi-threaded, and Valgrind is not multi-threaded. So yes?
Valgrind also, at least recently, didn't support some modern instruction sets. So ABS was like not ABX, sorry, was not supported about that.
Yes, Valgrind also doesn't like some of the instructions. It may support them, but very slowly. Yeah, but I don't want to blame Valgrind. I actually love Valgrind very much. But we are at least 10 times faster, and we do detect some bugs that Valgrind doesn't. Vice versa is also true, in fact. The tool has moderate memory overhead, typically 2x, slightly more. We have been using this tool inside Google, and we have users outside of Google for more than 3 years now. And we found at least 3,000 bugs in Chromium browser since that. Maybe more. And we found comparable number of bugs in Google server-side software. What I like to tell everyone even more is that we have lots of users in the open source community. Firefox uses us very actively, and there are lots of large and small projects that find bugs with this tool.
Question?
Yes?
Like anecdotally, what percentage of bugs would Valgrind find that this does not find?
What percentage of bugs will Valgrind find? None, because in most cases you cannot run huge applications on the Valgrind. It just doesn't scale. When you can run, Valgrind will find everything related to heap and almost nothing related to stack and globals. It just cannot do this. But we found that you just cannot run full Chrome browser on the Valgrind in reasonable time. It just doesn't work.
One more question. Compared to Purify, which is, I'm old, Purify was my friend. Tell me how this compares, the three of them, to Purify.
So Purify. Last time I tried Purify, I compared it to Valgrind because there was no AddressSanitizer at that point. And Valgrind was beating Purify in all possible benchmarks. I haven't tried Purify since.
As I said, I'm old.
So I want to say a few words specifically about Chrome. Chrome developers were the first users of ASan. It was May 2011. In fact, my team is part of the Chrome team, so we developed this tool because we wanted to help the Chrome folks. And now, 3 years later, all the tests that Chrome has are being executed with ASan 24/7 on the buildbots regularly. But since the tool is dynamic, your testing with ASan is as good as your tests. And the Chrome folks developed a massive scale fuzzing infrastructure, which they call cluster fuzz, which generates random tests on the fly, throws them into instrumented Chrome, waits for like 10 seconds. If nothing happens, it goes on. And just this testing infrastructure alone has found over 1,000 bugs at least. It also can minimize tests, deduplicate tests, find regression ranges, and verify if the bug is fixed. Another part which I like about Chrome and ASan, that there is a significant amount of external folks, non-Googlers, who do the same for Chrome. They find bugs, they report them to Google, and they actually get some bounty for this. And all this is using AddressSanitizer. Then I could have duplicated this whole slide, replacing Chrome with Firefox. Firefox Mozilla does exactly the same. And they also find a remarkable amount of bugs in their browser. Let's move to something more complicated. Concurrency bugs. We have a tool for concurrency bugs. We call it ThreadSanitizer. And it basically detects data races and deadlocks. A couple of few less interesting things too. Again, it uses compile time instrumentation. Again, LLVM and GCC, both major compilers, open source. The compiler part handles reads and writes. And the rest of the interesting stuff is going on in the runtime library. Here is an example of a data race. I used to show an example using pthreads, which was surprisingly simpler. So the example with C++11 has less code, but the report is more complicated because the code in Lambda translates into something incomprehensible. But still, I hope you get the idea. Data race is a situation when you access the same memory location in two different threads. At least one of the accesses is a write, and there is no synchronization between the accesses. And ThreadSanitizer will tell you exactly that. It will tell you that there is an access to some variable here, that before that there was another access to the same variable here. And in many cases, it will show you what the memory was, what the locks were held during those accesses, and some extra information. Again, the usage is very simple. You just compile your program with a special switch, either Clang or GCC, and run it. Here is a deadlock report example. We've implemented it recently. This is not rocket science, but you have it there for free. I will not stop on it anymore. So how does this tool work? Compile instrumentation is extremely simple. We just insert function calls before every interesting event in the program. Again, this tool plays tricks with virtual address space. Unfortunately, race detection is much more complex problem, so we need much fatter shadow memory. So we give the application just a tiny piece of address space. It's still several terabytes, and we map it to a 4 times larger part of the address space using, again, 2 arithmetic instructions. What do we store in that shadow region? First of all, let me define what we call shadow cell. Shadow cell is an 8-byte word which represents one memory access that has happened in the past. And as like half of the speakers on this conference mentioned, indirection is bad. And here you see we do not have any indirection. So this 8-byte word is a complete information. All you need to know about one particular memory access in the past. It is thread ID, like 16 bits or something. It is scalar clock, which is the huge thing, about 40 bits. Then there is a 5-bit position and size within the 8-byte word of the application. And then there is 1 bit for whether was it read or write. Let me show how does the analysis works. Remember, we map 8 bytes of the application into 4 8-byte shadow cells. Before we touched a particular piece of memory, the shadow cells are empty. Nothing is there. We don't know anything. When a first memory access arrives, and in this case, it is a write of 2 first bytes from thread T1. So we just record all this information into one of the shadow cells. The second access arrives. It is a read of the last 4 bytes in some other thread. So there is no intersection. These are disjoint memory regions. We just record this information into another cell. And then there is some third memory access, read of first 4 bytes from yet another thread. We record this information into another cell, but then we notice that there is an intersection between this memory range and one of the previous memory ranges. And now we have to decide whether the current memory access and the previous memory access have a happens before relation between them. And happens before relation is something that is created by synchronization, either mutex log, semaphore, or atomic synchronization. And this is what ThreadSanitizer is also monitoring all the time. I will not go into detail of how this is actually implemented, but the key point here is that checking happens before, in our case, is a constant time operation. It requires two memory accesses with 1 indirection level each, so very cheap. Oh, okay, just cheap. I will skip that. The ThreadSanitizer tool is much more expensive because the problem we're trying to solve is much more complex. Still, it has quite moderate overheads. On CPU, we typically see from 4 to 10x slowdown, and memory overhead is sometimes 5, sometimes up to 8 times. The tool also has collected quite a bit of trophies, mostly in Google so far. So there are many hundreds of data races in the C++ server-side code. And what I'm especially proud of is that this tool scales to huge applications. Like the biggest application we have at Google, we can instrument the full thing. We can run the full thing. It will be slow, but it will run and it will find data races.
Question.
Yes?
Does it understand atomics?
Yes. The question was, does it understand atomics? So if the atomics are written in your code using GCC built-ins, C++ 11 things, whatever like good way of implementing atomics, it will understand them. If you write atomics in line assembly, we'll have hard time. But yes, we have quite a few atomics in our code, and everything works. Although, of course, if you abuse atomics, ThreadSanitizer will be slower than usual because handling synchronization is actually quite expensive in the tool. What I didn't mention before, TSan is not C++ specific. This tool actually can target any other language that have data races in it. And we already implemented a variant for the Go language and found quite a bit of races there. Chromium is yet another customer. We have just deployed TSan for Chromium like a quarter ago and already found over 100 bugs there. With Mozilla, the story is a little bit worse. They've tried to deploy TSan in Firefox, and the developers were overwhelmed with bugs. And they say, okay, we have ASan, we have bugs from it, let us wait a little bit. They've also complained to us a couple of times saying, hey, TSan barks, and this looks like a false positive. And in all cases, that was a real bug in Firefox, not in TSan. Yes, this is a challenge. And this is a challenge for many tools like this, even including static analysis. That developers sometimes are scared by the number of bugs the tool finds, and they just go away. I don't want to see this.
When people get a lot of bugs, do they tend to be sort of the same bug manifesting in multiple different ways, or are those really distinct bugs?
So sometimes, yes, a single bug may manifest in many different ways. And usually, I just say, don't look at the whole stack of reports, just fix the first one, and then rerun. And especially for races, if you've missed a synchronization somewhere, you will have races on everything. Just suppose you forgot to grab a mutex somewhere. You will have a data race on one variable, on another variable, in some other thread, etc. So yes, TSan is not perfect in removing duplicates. It tries. It will remove a huge amount of duplicates, but not all of them. So the key advantages. TSan is not the only data race detector available for C++. But at least at the best of, as far as we know, it is at least 10 times faster than any other tool. And then, as Fyodor already asked me, the tool natively supports atomics, which is not true for at least Helgrind and Intel Parallels Inspector, which don't support atomics. So you don't have to do anything special if you have code full of atomics. There are also limitations. This tool today only works on 64-bit Linux. And it relies on atomic 64-bit load and store, which makes it very hard to port to 32-bit platforms. I'm not sure if anyone cares. And the other limitation of TSan is that this tool actually requires huge amount of memory. So if you're limited with memory, go do something else. Other set of...
Buy more memory.
Buy more memory. You cannot always buy more memory. One of our customers have the biggest machine in the world, like huge amount of memory. And their workload is very close to the limit, so they cannot extend it any further, just physically. This is not a question of money. But yeah, this is a problem. Another problem is that this tool doesn't instrument things like pre-built libraries or inline assembly. So first of all, it will not catch bugs there. And second, if atomic synchronization is done by inline assembly or inside pre-built libraries, it will not catch it. This is one of the reasons why, out of the box, it may produce false positives in C++11 programs with shared PTR. Because shared PTR has atomic synchronization, which actually sits in the libstdc++.so file, which we don't instrument. So the solution for TSan is to rebuild the standard C++ library with instrumentation. Then everything magically works. Let's go to the third tool, MemorySanitizer. We have finished implementing it and started deploying it just recently. So this is the freshest thing. This tool finds only one class of bugs, which is use of uninitialized memory. Again, the simplest program I could come up with, we have a stack variable, which we don't fully initialize, and then we use the part that is uninitialized. Again, you run the compiler with a special switch, and this time it is also only available in LLVM today, not on GCC. And you run the program. If the bug is found, it will tell you that there is uninitialized value, and it will also tell you where the uninitialized value is coming from. In this case, this is a stack variable, and it, as you can see, shows the name of the variable and the name of the function. If this is a heap variable, it will show you the stack trace of the heap allocation. Again, we play with the address space, but now shadow memory is extremely simple in concept. It is bit to bit. So we shadow every bit of the application with 1 bit of shadow. And if that shadow bit is set, if it's 1, it means that the corresponding application memory is dirty. It is uninitialized. There is garbage. Uninitialized memory comes from two sources. First, it comes from Malloc, or operator new. And second, it comes from local stack objects when they appear in the beginning of the function. The memory is being unpoisoned or initialized when something stores a constant into that memory. Now the tricky part. It would have been very easy to detect uninitialized memory loads if every load of uninitialized memory would have been a bug. But this is not true. One of the most frequent cases is structs with padding. Suppose you have a struct or a class or templated class, blah, blah, anything, which has a padding. No one initializes padding. It always contains garbage. But the compilers are often smart. They don't want to move 1 byte and then move adjacent 4 bytes, because these are 2 instructions. They want to move the whole 8 bytes at a time. It means that they're moving garbage around. And this is completely legal from the point of view of the language standard. So we have to tolerate this. And this gives us all the complexity of the tool. So when there, yes?
What about like SSE instructions that read a bunch of memory from main memory and then only actually use some of the bytes?
So what about SSE instructions? With SSE instructions, we are, so we tolerate copies when they're done with SSE instructions. And we actually tolerate some of the arithmetic in SSE, like vector, let me show this slide. This slide shows you few instructions that in which we propagate the shadow. So instead of complaining if there are initialized bits, we propagate the fact that some of the bits are initialized, and we assign the shadow to the result of arithmetic operation. Like if we shift B by C, we also shift the shadow of B by the same C. So we've shifted some of the bits of the application, and we take the bits of the shadow and we shift by the same amount. When we do bitwise AND, we do even more complicated instruction, because bitwise AND may actually clear something that has been uninitialized. So now it is initialized even though the operation was done on uninitialized bits, and so on. And we report an error only on some of the uses where this is actually a real bug, like conditional branch, when you use uninitialized bits for computing the PC, or when you pass the uninitialized bits to system call. Otherwise, if uninitialized bits have any visible side effect on the program. So this strategy, by the way, this strategy is very similar to Valgrind. Yes?
Well, why do you need bit to bit and not just bit for a single byte?
Why do I need bit to bit, not bit to single byte? Because there could be a byte which has some of the bits initialized and some not. Like you can take an uninitialized byte, and using bitwise AND, you can initialize a single bit in it. So that particular bit will be good, and the rest will be garbage. And this happens in C++ and C programs all the time. So we cannot just forget about it. Another funny reason why we need bit to bit and not bit to byte is data races. This tool is completely multi-threaded. It doesn't do any global lock, anything. It runs at full speed in all threads. But if you have small amount of shadow per large amount of memory, you will end up writing into the same shadow when you are updating different parts of your application memory. And you will have data races on shadow. You don't want this. Valgrind uses 2 bits per byte. And they don't have this problem with data races because Valgrind is single-threaded. But you don't want to trade bits of shadow to single-threadedness. This is really bad for performance. So this strategy with propagating bits is actually quite useful because it allows us to avoid false positives. But now often users don't know where did the uninitialized memory come from. Just don't know. Suppose this example. You have 2 heap objects that come from different mallocs on U or whatever. Then you do some kind of arithmetic on these objects. And at this point, you cannot report a bug because of what I have said before. And then sometime later, you use the result of that computation in a conditional branch. And MemorySanitizer will tell you, this is an uninitialized memory read, but who is guilty? Until about 5 years ago, this was a nightmare. No one knew how to debug these things. Then Valgrind has implemented track origins flag, which actually propagates the origins of the poisoned memory alongside the shadow. And this feature is very useful. You can actually see what memory was not initialized. And we've used a similar strategy. We assign a 4-byte origin ID to every 4 byte of application memory. So this uses one extra part of address space with one-to-one mapping. And it brings 2x additional slowdown. I wonder if anyone sees this slide. So we have implemented what we call advanced origin tracking. It helps in cases when you load uninitialized memory and you copy it, and you copy it, and you copy it, and you copy it, and then you use it. In that case, even the Valgrind-style origin tracking will not help you because you don't see how that uninitialized memory has arrived to this point where you use it. And we have implemented, just recently, we have implemented a mode which actually shows you the whole history of this memory being copied around. And this slide shows you how the virtual memory is organized in the tool. So we divide the whole thing into 4 pieces. One belongs to the application, one belongs to the origins, and one belongs to the shadow. And there is the fourth one, which is completely unprotected. No one can go there. The overhead. This tool is actually quite fast. In the default mode, when it doesn't track origins, it is roughly 2.5x slowdown and exactly 2x memory overhead. With origins, everything doubles. The tricky part. So if one of the first 2 tools doesn't instrument something, it will simply not find bugs there, but nothing bad will happen. If MemorySanitizer doesn't instrument something, it will not see a write to some memory and will complain that this memory is uninitialized, even though it is. So it has to observe all writes in the program. And this makes the tool harder to deploy compared to other tools. So for example, libc, we don't instrument libc. For that we have solution. We just wrap all the interesting libc functions. And because libc is kind of fixed thing, we just know the interface, we know what the functions are doing, and we tell MemorySanitizer that this libc function does that. Again, the problem with inline assembly, and that problem we don't have solution for yet. We just simply have to disable inline assembly where possible. And then there are JITs that generate code on the flight, which we don't instrument. This is painful, but at least we solved this problem for Chrome, which uses JavaScript JIT called V8. Still, we use this tool in several large-scale projects. First, just to give you a taste, we've tried the very early version that barely worked on a proprietary console application, more than 1 million lines of C++ code, which has not been tested with Valgrind before. Some piece of code which we supposed may contain bugs. And we found 20 unique bugs in just 2 hours. Then we've run the same test suite on the same program using Valgrind. And Valgrind has found the same set of bugs, but it took more than 24 hours. Just to give you an idea of the real-time usage. And MSan actually produces much better reports when the uninitialized memory comes from stack. So the analysis was simpler.
Question?
Yes.
Did you say it caught all of them?
Valgrind caught all of those
No,
bugs.
the one, when you ran the program on what Valgrind caught, did your program catch all of them? In other words, is.
Yes, the set of bugs that Valgrind and MSan found on that particular case is the same.
There's no exactly the same.
Exactly the same. So Valgrind also finds addressability bugs, but that particular program has been tested with AddressSanitizer very extensively, so there were no easy to find addressability bugs left. So there were only uninitialized memory reads bugs, and Valgrind and MSan had exactly the same set of bugs found. But the time required was more than 10 times less for our tool.
The reason I'm asking is it's so surprising that the set of bugs is identical. That's unbelievable.
Well, the approach is very similar, except that MemorySanitizer uses compiler instrumentation, where Valgrind uses binary instrumentation. Otherwise, the approach is very similar.
Fair enough. Okay.
Then we deployed this tool for the LLVM compiler, the project which helped us create all those nice sanitizers. And we found over 20 bugs in LLVM so far. Those were not bugs that existed in the source for ages, because LLVM is also being tested with Valgrind periodically. But those were regressions caught by regular bootstrap. And the bootstrap with MSan takes about an hour and a half. And you cannot possibly do this with Valgrind, because bootstrap will take more than 24 hours. This is just too long turnaround for the project that develops very fast. And the developers are reported about the bugs in an hour or two after they commit them. So this just speeds up the development process. Also found many hundreds of bugs in Google's server-side software and in Chromium. Okay, this is last of the sanitizers I want to describe. It is not last in time, though. It has been there for a while. It finds various what I call simple bugs. And by simple, I mean really simple, like integer overflow. This is not a rocket science to find an integer overflow, but LLVM developers collected a lot of undefined behavior checkers under the same roof of UBSan. I will just give you two examples. This is an integer overflow, and if you run it with UBSan, and again, to run it, you need to compile it to the special switch and run the application. UBSan will tell you the exact source file and line location, and will tell you what the values were and what the bug is. The second example is shift by invalid value. Like you cannot shift 32-bit integer by something more than 31. And the tool will tell you exactly this. So the main challenge with UBSan, and it is even more challenge with UBSan than the previous tools, is that it finds too many real bugs. You just cannot enable it on a huge code base at once. You have to cut the dog's tail in small pieces. For tool developers, this is a good problem to have. But since we're also tool deployers, this is a hard problem to solve. And this tool allows you to enable a subset of checks at one point. And here is, I suppose, almost complete list of the checks. The tool is actually very simple. It doesn't use any tricks with shadow memory. It doesn't replace the allocator, etc. And it has very moderate slowdown. Typically between 0, you don't see it, and 1.5x. Wrapping up, I have like 8 minutes. So current status. ASan is the oldest of the sanitizers, and it works more or less everywhere, including Linux, Macintosh, Windows, Android, FreeBSD, iPads, iPods, whatever. We can actually run ASan on this kind of device, and we do find bugs with this approach. TSan exists in two major open source compilers, but it only supports Linux 64-bit x86. MSan is even newer. Today it exists only in Clang, and also only supports x86 64 Linux. UBSan is simpler to port anywhere, but we didn't try to do it yet. So it is currently in both compilers. we use it on Linux x86-64, and someone uses it on OS X. By the way, we have ASan for the Linux kernel. This is a completely separate project because kernel is a completely separate environment, and it doesn't have anything to do with C++, but we still have it if you're interested. A few words about deployment challenges. As I've mentioned a couple of times, but I want to stress it again, the real bugs that the tools find is the major challenge. This is a good challenge to have, but we have it. The second challenge is benign bugs, and especially benign races, even though there is no such thing. There is no such thing as benign race, but many developers, for some reason, believe that there is. And here is a link to an article which we use to show the developers that they're wrong. Of course, the overheads is another kind of challenge. And we find that the memory overhead is usually a much bigger challenge than the CPU overhead. Because CPU is something you can just wait for a little bit longer. And memory is something that you just may not have. And the problem ranges from small devices like this. Like, we cannot run Chrome on Android with 1 GB of memory. It just doesn't start. We can run Chrome on Android with 2 GB of memory. Or maybe you have virtual machines with limited amount of memory, and if you want to put the sanitizers there, you have to increase the number. CPU overhead is much smaller problem, but it just adds a cost. So if you run longer, you eat more electricity and CPU time, etc. One of the major challenges I'm faced with now is to run sanitizers in production. As we see from our experience, most of the bugs can be caught during testing, but some small fraction cannot be caught in testing. And we've run few projects in production, and we found that short tail of the scariest bugs. So I know that there are some folks from compilers, from compiler development teams outside of LVM and GCC crowd, and I want to ask those folks, please implement the sanitizers, or at least AddressSanitizer, in other C++ compilers. It is very simple. ASan compiler model is about 2,000 lines of code, and this is all you need to do. The runtime library is BSD-like licensed. You can just take it. And the final slide, I want to say some general words about the future. I think that the C++ software engineering community has to embrace the idea that if you want high-quality code, and if you want it to be tested, checked, and compiled efficiently, you have to compile everything, just everything, so that the only thing you don't see inside are the system calls. This way, you will get full coverage with all the sanitizers. You will have full coverage with all the existing static analysis tools. And this way, you will benefit from whole program mode optimizations. Here are the links to the tools I've mentioned. And here is a quiz in case you don't have a question. Find all the bugs here. Thank you, and I'm ready for questions.
I'm your biggest fan. I say this to all of the hundreds of nooglers that I offer training to, and now I'm saying it to all the hundreds of you. If you have a crash and you're not running these tools, you are solving your problems slowly and inefficiently. Right? This changes the landscape completely. If you are not reevaluating your tooling strategy in light of the fact that it is 10x faster, I don't know what it would take to make you do so. Right? Go grab this. If your stuff builds with LLVM or with GCC, go grab this. Like, do it tonight. Thank you, Kostya.
Thank you, Titus.
I had a question about TSan. I'm sorry, over here. Your looking at your data structure, it looked like it was able to store the last access for, and you just stored the thread along with that. How is it easy to hide a race condition in TSan? Like if I do a write and then a read on the same thread and then a read on the other thread, would that mask that race condition?
So the question is it easy to hide data races from TSan? It is not easy, it is possible. So the worst thing you can do to hide data races from TSan is to use a lot of unrelated synchronization. Like if you have lots of stuff that does synchronization for itself, it may hide data race on a particular run of the application. If you run it several times, it will still be uncovered. What you say is that what happens if I write to a memory location that then I read from that memory location? This has much smaller chances to hide data race, but it still has.
Thank you.
My name is John Lakos. I work at Bloomberg. And I want to tell you that this kind of stuff has taken me a very long time to convince management that is worthwhile. However, I am lucky enough that about 15, 16 months ago, I was able to hire a very senior guy from Google to do this work for me. Not exactly this work, but actually static analysis takes away about, I'm going to say 50%. I might be exaggerating. But if I say 25%, I'm lying. About half of the work that people need to do when they review peer code can be handled by static analysis. And better. Would you agree?
I am a fan of dynamic analysis. But yes, of course.
Whatever. And so I completely, you're right. You do handle that. I apologize. The point being that these kinds of tools are really, really important and take away from the time that is consumed by other people working on redundant review that doesn't need to be done. So I completely agree and support. And I want to actually ask you, how do I partner with you?
Everything is open source. We have mailing list. You try. If something doesn't work, send us an email to an open mailing list.
So anyway, I just really support you and thank you so much for all of this. This is awesome. Awesome, I tell you.
Thank you.
Do any of the tools, or all of the tools, have a way of annotating the source code to tell the tool, the back end, that something interesting is going on? For example, if you write your own memory allocator, you want any of the sanitizers to know that this is now raw, uninitialized memory, and when it's freed, it's now in that state. Or the situation I was thinking of is you mentioned, if you resize the vector, it somehow the tool knows that the elements off the end are bad, but I don't know, how does it know that since they've been allocated and they've been initialized at least once?
Yes, thanks for the question. I will start from the end. So indeed, to find these container overflow bugs, we have added a single annotation in multiple places in lib C++ code. And we have the same version for the same annotations for libstd C++ code. So the source code of the C++ library have to cooperate to find this particular kind of bug. We have annotations to say that this memory is poisoned or unpoisoned for ASan and for MSan. And for TSan, we have annotations saying that this is a synchronization, even though you don't see it. So yes, you may instrument things like, you may annotate things like free lists, but if you can avoid free lists, it will be better, because the tool knows better how to find bugs than your free list. Because your free list will not have proper quarantine, it may not have proper red zones, etc. But you may do it. Thanks for the question. Okay, we've timed out. Yeah.
Hi. I will admit I don't have a question, but I was waiting to make sure that there weren't any other questions. I just wanted to point out two things. One, we spend a lot of time trying to deploy static analysis tools at Google, especially on Chrome and in other parts of Google, and they were a disastrous failure. And they weren't a failure because they didn't work. They were a failure because developers didn't actually fix the bugs that they found. There are lots of reasons for that. We could have a whole talk about why that happens, but that's the reality of static analysis tools today. I hope that we get static analysis tools that don't have this problem, but we don't have them yet. That's not the case here, because every single report is a bug, and not like a hypothetical bug either, but like a bug that was hit in a run of the program over an input that it was expected to work on. And the consequences are just a radically different perspective for every single developer in the company. I'm actually of the opinion that the sanitizers are the single most important development in C++ programming in the last 10 years. So if you think this is just important about being more productive, no, it's actually a model change. The primary advantage that Java has had for a long time over C++, one that I actually understood, was safety. And with the sanitizers, I see that gap closing. And so I think in particular if you're concerned about safety, security, or the rigor of your software and you're not running sanitizers, you really have to start running the sanitizers. Please do. Please email if there's some reason you can't, because it's more important to get everyone using these sanitizers for C++ than anything else. Because people have to understand that C++ can be a safe language again when we have these kinds of tools. So again, thank you, Kostya.
Thanks a lot.